All right, so let's go ahead and take a moment to go over the square plane of the last of the octahedral domain. Octahedral domain, remember, has 6 electron domains, bonding or non-bonding domains around the central atom. So this is xenon tetrafluoride. Let's take a look here. How many valence electrons for xenon? 8. And the fluorines are 7, and there's 4 of them, so times 4 is 28. This is going to give us a total of 36 valence electrons to work with. So, now, which one's going to go in the center? Xenon is going to go in the center. We will attach the ligands. 1, 2, 3, 4. I have just used 8, so now I'm down to 28 of my electrons. Satisfying the octets of the fluorines, that's going to be 6 valence electrons each. There's 4 of them, so that's 24. So let's go ahead and put those on. So that gives me 4 left over. And what do I do with leftover ones? They go on the central atom. Okay? So this one's a little tricky in order to visualize. Let's take a look at the 3D model, the ball and stick model, to get a good idea. Okay, so looking here, what you should see is basically, if I tilt it a little bit, you see the lone pairs. In order to spread out and be as far apart as possible according to VSEPR theory, one will be on the top and one will be on the bottom, which creates this flat square. Okay, so we have a flat square. This one's also kind of an exception, interesting feature type molecule, because if you're looking at it in terms of the symmetry here, it looks very symmetrical. And all the dipole moments are going to point towards the fluorines, right? So what type of molecule is this going to be, polar or nonpolar? So it's going to be nonpolar due to the fact that it's very symmetrical, even though it has lone pairs on the central atom. What you need to make sure that you're doing is looking at the symmetry, and so square planar and the bipyramidal form of linear under the bipyramidal domain. Those two have lone pairs on the central atom. And if the ligands are the same, like in this case where they're all fluorines, okay, you're going to end up having the dipole moments cancel, and it's going to be nonpolar. Those are the main exceptions for the lone pair idea. Pretty much anything else that has a lone pair on the central atom is going to be polar because the dipole moments shouldn't cancel. That's the bent ones and the trigonal pyramidal ones, the seesaw, the T-shapes. Okay, the other ones that have lone pairs where it's not going to be very symmetrical, those ones, of course, end up in the polar category. Now, looking here, you should be able to easily figure out what the bond angles are going to look like. They're all going to be what? 90s, yes. So if we tilt it a little bit, you'll be able to see the bond angles there. 90-degree bond angles for our lovely square planar example. So let's go back here and finish up. So we have the dipole moments, although they all go towards the fluorines, and we do have 2 lone pairs like so. This is going to be nonpolar. 90-degree bond angles for each of the F to the xenon to the F bonds. And we have what type of bonds here? We have 4 sp3d2 sigma bonds. Very good. So that will end up with this last structure here. Do remember that the hybridization of the bipyramidal and octahedral domain, those ones will not be tested on, but they will be in the problem set because the book doesn't delineate the fact that it's not on the AP exam. So you will see them in there. All right, let's talk about large molecules and the ball and stick molecules too, as you see here. Because you have to be able to kind of go in between the Lewis dot and the ball and stick models here. All right, so this one is showing us CH3COOH. This is the chemical formula for ethanoic acid, also known as acetic acid, also known as vinegar. So a bunch of different things here. But looking at this ball and stick model where you have more than, you don't have one simple central atom here. This one has more than one central atom. What you'll notice too is like the black circles are usually going to be the carbons, okay? And the red ones will be the oxygens. And then usually in the models, the white, smaller ones are going to be hydrogens, okay? And there is a problem in the problem set, that's why I'm going to go over this, that you need to realize they don't always, on the ball and stick models, draw in the lone pairs for you. So you have to kind of visualize the lone pairs yourself. Or you could go and draw the Lewis dot structure, that's fine as well. However, what do you know about oxygen usually? If it's going to be following the normal rules, it's going to have 2 bonds and 2 lone pairs, right? So you could visualize the fact that these should have lone pairs on them like so. And then you would know that this is 1, 2, 3, 4. This is still in the tetrahedral domain. It's under the bent shape. So this part of the molecule, okay, you could isolate and look at this particular oxygen in the center there and be able to tell the shape, the hybridization, and the bond angles on that portion of the molecule. Does that make sense? And then like here, this portion right here around this particular carbon is going to have a different type of geometry, right? Makes sense here. So this one has 3 bonded atoms, no lone pairs on it, because we count the bonds 1, 2, 3, 4. There's 4 around that carbon. So 3 bonded atoms, no lone pairs. What would be the shape around that particular carbon? The T-planar shape, yes. Okay, and then you could do the hybridization and angles off of that as well. So that's kind of the basis here of if you see it represented as a ball and stick model like that, be aware that not all ball and stick model representations put in the lone pairs, so you just kind of have to mentally do that yourself. But I do have another example where they give us the Lewis dot structure. Okay, like here, you have the full out Lewis dot structure. It's a big organic molecule. But they might like point to one particular atom, one particular element, and you're supposed to tell the shape, the hybridization, the angles, and the geometry around it. I picked out 4 for this particular example. Okay, so I'll do the first one with you, the blue star over here. This blue star carbon. Okay, if you look at the blue star carbon, what do you see around it? How many bonds? 4 bonds, no lone pairs. So can we identify that shape? It's going to be tetrahedral. Very good. This one's going to be tetrahedral. Right? And what do we know about the bond angles for these ones, whether it's the O to C to C or the H to C to H bond? Like, because we could go this way, or we could go that way. Doesn't really matter. Any of those bond angles around that central carbon there, what is it going to be? 109.5 degrees. Good. All right. And what do we know about the hybridization here? sp3 sigma bonds. Good. And yes, there'll be 4 of them. But if it just says identify the hybridization, you don't have to say the number. If it says, identify the number and type of bonds in there, because some of them might be different, yes. So we have sp3 sigma bonds here. Tetrahedral domain, 4 domains means 4 orbitals are going to merge to form the hybrid. Remember, the whole merging and forming the hybrid is to put it at a slightly lower energy state. So that's the purpose of it. So I'm going to give you like a couple of minutes here to work on the other ones real quick, and then we'll go over them. All right, let's take a look here at the purple star. This purple star one right here, which is going to be about oxygen. So we see we have 2 bonds here. We have 2 lone pairs on the oxygen. So what would that shape be? That is definitely bent. It's under the tetrahedral domain because it has 4 electron domains, but it is the bent shape of that domain. And what do we know about the bond angles of the bent shape? Less than 109.5. Or if you put 104.5, that's fine. That's also would be acceptable. 105 would be acceptable, I'm sure, as well. And what is our hybridization here? sp3 sigmas as well, because it's under the tetrahedral domain. Very good. Let's look at the green carbon over here, this green starred carbon. We have 1, 2, 3, 4 bonds around that carbon, so 3 bonded atoms, 3 domains, and that's going to be which shape? The T-planar shape. Very good. So what are the approximate angles for a T-planar? 120. Very good. And what are our type of bonds here? Because we do have 2 types here. sp2 sigmas. Very good. And due to the double, we have, yes, 1 pi bond. Exactly right. Our last one up here, being the nitrogen, okay, 3 bonds, 1 lone pair. What's our shape for that one? The pyramidal, T-pyramidal, yes, that would be correct. Pyramidal. All right, and what is the bond angle for the T-pyramidal? Less than 109.5 because it's in the tetrahedral domain as well. We have the 3 bonded atoms, 1 lone pair. Ideal bond angle is 109.5, but it's a little bit less. You could also put approximately 107. They would accept that as well. And what type of bonds do we have here? sp3 sigmas, correct, for that particular one. Very, very good. So this is one example where they give you a large molecule and you have to hone in on one particular central atom, figure out the shape and stuff around that one particular spot on the molecule. Now this is another version of a question they can use with that, continuing on the free response. Oh, never mind, we're not there yet. Here's the answers. Yay, okay. We got them right. All right. This is another thing they could tap on to the large molecule type problem in the free response. Kind of pull some of the information back from the first set of topics in the unit. Rank the bonds in terms of decreasing bond lengths. Okay, and then looking at which one has the greatest bond energy and which one has the least bond energy. Now, what do we look at for decreasing bond lengths? What do we need to really focus in on in terms of our bonds? What? There's a couple of features we need to point out here. We have 2 things to look at. When you're trying to determine a bond length, what do you need to look at? The number of bonds. Good, heard that somewhere in there. And what if they're all single bonds? What do you compare there? The what? Bond length's going to be determined by what? The size of the atoms, right? And yes, all those things you were saying have to do with the size of the atoms. And yes, you would look at the proton number and things like that and comparing which ones are smaller, which ones larger, but you need to hone in on looking at the sizes of the atoms by using those periodic trends that we were talking about that affected nuclear charge and things. I heard a lot of people saying stuff like that. Very true. So the first thing you should do also, make sure that you have the decreasing in mind. So that means we're going from largest to smallest, okay? Always put that in my head so that I don't get them out of order and go reversed. But right here, let's list out our bonds. We have the C to O, that's this one right here, okay? We have the, we have this one right here, so that's going to be a C to N. We have this one right here, which is a C to C. And we have this one right here, which is a C double bonded to an O. Now, out of those four, which ones are going to be on the larger side already that you can just pick out immediately? The ones that are going to be larger are going to be the single bonds, right? Okay, so now we need to look at these two and compare them. So we know double bonds and triple bonds get smaller in length. So out of that, we have two carbons in the bond, so that's great. Those are the same, but the oxygen and the nitrogen are different now. Comparing the size of oxygen and nitrogen, which one is a larger atom? Nitrogen's a larger atom because it has one less proton than oxygen, and therefore it's going to be just slightly larger. That's going to make the C to N bond length just slightly larger, right? So that one's going to be our largest, right? The C to N. Then what comes after the C to N? The C to O. Okay, now let's deal with the double bonds. We know double bonds are shorter than single bonds, so they come next. Once again, comparing, both of them have a carbon in them, but the other atom in each bond, one's a carbon, one's an oxygen. So out of those, which one is the larger size? Which one's the larger size? Carbon's going to be larger. Carbon has two less protons than oxygen. So just going to have a little bit more space for that. Therefore, the C double bonded to the C is going to be slightly larger than the C that's double bonded to the O because the O is a little bit smaller in terms of the size. So this is kind of how the bond length is going to go. We have the largest over here to the smallest over here. Now, what do you remember about bond length and energy? Smaller the bond, the greater the energy. Okay? Greater energy means what about the bond? Well, besides that, it's smaller. It also means it's stronger. Very good. So smaller bonds are stronger than larger bonds. Very, very good. So which one's going to have the greatest bond energy? Okay, this one over here is the greatest, right? Greatest bond energy. And the one with the least bond energy, okay, is going to be the longest, which happens to be the C to N. So this one's going to have, this is the least, like so, and this one's going to have the greatest bond energy. Exactly right. So this is kind of how one of the three responses could look, where you have to identify some VSEPR stuff off of it and then go into talking about the bond energy and bond lengths. Comparing them, of course, qualitatively, although you could be given tables like the bond length table and then extrapolate the bond energy and stuff like that, as you've seen in the problem set and on the quiz. Very good. All right, so quick little thing about rotations, pretty simple. Sigma bonds can rotate around the axes, but pi bonds, because they're overlapping p orbitals in the pi bonds, they do not have the ability to rotate So you will not see any rotation ability across a double or triple bond. But as you can see here with this particular one, you can see that this molecule can spin and rotate on the axis that later on will give it, you know, a little bit more features in terms of having a little bit more entropy, but we'll get to that aspect later. All right, off to formal charge now. Formal charge is important. This is a new added extra thing for AP. The reason, or what we've been drawing throughout our whole section of notes here, is actually the formal charge best Lewis dot structures following the rules. And the rules were designed to basically follow formal charge ideas. But sometimes it's not that cut and dry, you know, especially when you're dealing with some of the expanded octets or some of the polyatomic ions where it's a little bit more complicated. All right, so for each atom you have to count the electrons in the lone pairs and half the electrons it shares with other atoms. So basically each bond counts as one, each dot counts as one in terms of the electrons assigned to the atom. So you figure out the valence electrons for each atom in the Lewis dot structure. You subtract the electrons that are assigned to it in the Lewis dot structure, and you get the formal charge numbers. Okay, so that's the basic idea here. We're looking at the carbon dioxide example, and I showed you this earlier in the notes that this is why we wouldn't draw it like this, where we have a triple and a single. We look here, the valence electrons, oxygen is 6, carbon is 4, oxygen is 6. But the ones that are assigned to the atom, 1, 2, 3, 4, 5, 6. So 6 are assigned to our oxygen over here. So you subtract and you get your 0. This would be for the carbon, 1, 2, 3, 4. Okay, we subtract and we get the 0 there. And then for this oxygen, 1, 2, 3, 4, 5, 6. Subtract that, you get the 0. All the formal charges come out to 0, and you really want it to come out, as many of them to come out to 0 as possible in order to get the correct Lewis dot structure. If we look at this example of this drawing of carbon dioxide, still have 6 assigned to our oxygen over here, but 1, 2, 3, 4, 5, 6, 7 now are assigned. That gives us a -1 for the formal charge. The carbons are fine because it still has the 4 bonds around the carbon. Subtract that, that one still stays at 0. But if we look over here at our other oxygen, 1, 2, 3, 4, 5, 6, 5, 1, 2, 3, 4, 5 assigned, that's going to give this oxygen a +1. Oxygens are considered to be, you know, highly electronegative. So assigning it a positive charge does not seem like that would be a good idea for a highly electronegative element. If anything, they would be more on the getting the negative charge because they would be attracting electrons to themselves. Yes?
Can you explain how you get the first row of numbers?
Those are just the valence electrons of each atom. So oxygen has 6, carbon has 4, oxygen, so just the valence electrons, that's all you got to do. Then you count the assigned ones. All right, so we would choose to use the first structure because it gives us better formal charge. Remember, I just said formal charge, you want them to be you want the atoms to be as close to 0 as possible. Now, it doesn't work out all the time where they all end up being 0. So we're going to go over a few rules with that. Best Lewis dot structure is the one that has most atoms' formal charge is closest to 0. And like if you can't get all of them to 0, the next thing you should look for is putting a negative charge on the most electronegative atom. So that is the other thing that you want to do here. So try to get them to 0, but if you can't get them all to 0, then you want to make sure the negative goes on the most electronegative atom. Okay? All right, so now we're going to spend some time drawing some and looking at the formal charge here. So cyanate, NCO minus, okay? There's a couple different structures for this. And I'll just go ahead and draw one, and then we will add in the other possibilities, so we won't spend too much time on this. So we have our, nitrogen has 5, the carbon has 4, oxygen has 6, and then we have to add in, for the -1, 1 electron. So that's a total of 16 to work with, correct? All right, so looking here, it is written NCO, and out of those, the carbon is going to be the least electronegative, and it kind of puts it in order for you, but you want to put the carbon in the center. So we put the carbon in the center, we attach the ligands, oops, not as, attach the ligands here, okay. And looking here, I used 4 of the, so now we're down to 12. Satisfy the octets of the ligands like so. And we end up running out of electrons, right? Now, anybody make a suggestion of how to fix our carbons situation? Double bond on both sides. That sounds like a reasonable idea, so that's what we'll do. We'll take one off of here. Double bond that side. Take the one off of here. Double bond this side. Does that work? Does everybody have 8? All right, and then because this is a polyatomic, we would add the brackets, and we would put the charge outside. So that's one particular structure you could draw off of this. There are other possibilities though. So here, we did the one in the center. We did that one together. Some other possibilities would be this one over here to the left, where they triple bond the oxygen, right? Single bond the nitrogen. So this is an option. Okay. Or we could have gone the other way, and we could have triple bonded the nitrogen and single bonded the oxygen. So write those down, because we need to figure out which one of these 3 is the best based off of formal charges, and decide which structure is the one we want to use. So take a moment to write those down. Then we're going to set up our little chart so we can count our valence electrons, subtract our assigned electrons, and get our formal charges. So if we go here, I kind of just make a row. Here's the valence electrons. 5, 4, 6, 5, 4, 6, 5, 4, 6. Now in AP questions, for formal charge problems, they usually give you the drawings, and you just have to count, figure out which one's the better drawing. Sometimes too, they will give you the layout of the atoms themselves and tell you to fill in the dots, making sure that you're drawing the best Lewis dot structure based off of formal charge. So if you follow the Lewis dot structure rules, typically gonna get it in the right formal charge anyways. You can always count afterwards to make sure your formal charges come out the best. All right. So now let's start counting our assigned electrons. So for this nitrogen, how many are assigned over here? 1, 2, 3, 4, 5, 6, 7. So subtract 7, okay? This one's 1, 2, 3, 4. I'm going to subtract 4. 1, 2, 3, 4, 5. Subtract 5. So this is going to give me -2, 0, and +1. Let's look at this one. 1, 2, 3, 4, 5, 6. So -6. That's what? -1. 1, 2, 3, 4. So -4. 0. 1, 2, 3, 4, 5, 6. -6. 0. And last but not least, over here to the right, we have 1, 2, 3, 4, 5. That's 0. 1, 2, 3, 4. And 1, 2, 3, 4, 5, 6, 7. Very good. Now, do any of them have all three as 0? No. So we have to look at the most electronegative element. Which one's the most electronegative element?
Oxygen.
Oxygen. Okay. Well, we could probably just discount this one out because 2 of them aren't 0. Whereas in the other 2 over to the right, at least 2 of them reach 0. Okay. So it's really the competitions between these 2. Because that one had 2 that were not 0. Out of here, the middle one puts the -1 on the nitrogen. The one on the right puts the -1 on the oxygen. So, which one's the better structure? The one on the right, because oxygen is more electronegative, and therefore the best Lewis dot diagram for this particular structure would be the one on the right. And you would have to explain, you would say, these 2 structures have 2 out of 3 that reach 0, but the one on the right has the -1 on the oxygen, which is the most electronegative element. And that would be how you do formal charge. Alright, so let's talk resonance real quick, and then we're going to do a combined resonance formal charge one here. Delocalized electrons, that's the key word. It's very similar to the metallic bonding where, they detach and delocalize, whatever. Except for it's really in like these pi bond spaces where the p orbitals overlap. So to accurately draw these, you have to represent all 3. And what you should see here, of course, is a rotating double bond throughout the structure. So this is the one for nitrate, where it's rotating between the NOs, showing all possible structures. So what do we mean by delocalized here? The pink clouds are representing the p orbital overlap, because they are the dumbbell-shaped orbitals. And as you can see in the top diagram, this would just be localized, where it's only between one N and one O. Delocalized means now that extra pair actually spreads equally across all of the p orbital overlap. Just like you see here. So it kind of does like a blending. In a way, it kind of hybridizes those p orbital overlaps and allows the electrons free movement to equally space themselves and spend time across all of the NO bonds. So really, what is that telling us? It's telling us that extra pair of electrons is being equally shared. So each one really has like 1 1/3 bond of electrons. So the bond order would be like 1.33 due to that delocalization. So resonance really like kind of splits that bond across all that it's going to rotate with. Okay? Any questions on that? All right, now we're going to look at drawing fluorite. Now I caution you too, when you start drawing fluorite, you do need to consider formal charges. Okay? So take a moment to look at the possible drawing here of fluorite, and we will come back in just a minute. Okay, so let's go ahead and draw this real quick. Fluorite is ClO2 minus. We have 1 chlorine that has 7. We have 2 oxygens, that's 6 times 2, so that's 12. And then we have a -1, so we have to add in an electron for that. So it's a total of 20 to work with, correct? All right, so let's take a look here. We would put which one in the center? The the chlorine would go in the center. We would attach the ligands. Very good. All right, so I've used 4 down to 16. And now we satisfy the octets. So that's now going to put us down to 4. And where would we put the extra electrons? Central atom, like so. Which makes sense. However, this is not the best drawing for fluorite. Let's look at why this is. Okay. We have 6 valence electrons with 7 assigned here, right? That's a -1. We have 7 electrons, valence electrons, with 6 assigned here. When we subtract that, this is going to be +1. And then we have 6 valence with 7 again assigned, that's -1. None of these come out to 0. So this would not be the best structure for chlorite. Now, in all likelihood, you would never have to generate this on your own. Like, they would give you different structures to compare rather than you generating it. But what could we do here to improve our formal charge? We could do a double bond on one of them. So let's go ahead and do that. Let's go ahead and double bond the oxygen over here on this side. We'll do that one. So that means this only has 2 dots, right? And we have Cl and then we have our other oxygen over here, like so. Okay, let's check this and see what happens here if we do this. This, of course, results in the 6 minus 6. This is going to give us 7, 1, 2. What? But I took the lone pair off the oxygen. I didn't take it off the chlorine. I took it off the oxygen to create the double bond to make the oxygen's formal charge better. Does that make sense?
Yeah.
Because if you see, look now what it did to the chlorine's formal charge as well. So we have 1, 2, 3, 4, 5, 6, 7. It actually improves the formal charge on the chlorine as well by doing the double bond that way. So this goes to 0, right?
Yeah.
And then over here we still have the 6 minus the 7, so this is -1. So this is a much better drawing for our chlorite than the original one. Does that make sense? Now, like I said, I don't think you're going to have to generate it yourself. You just would have to compare different structures. But by drawing it this way, what happens now? We have resonance because that double bond can be on either side, right? So to complete the structure, you would draw the other one, okay? You would draw the other one here and do the double bond on this side, the single bond on that side, and add in our dots, like so. And now we have resonance because we corrected it to make it a better structure based off the formal charge. So some of these polyatomic ions, when you Google them and look at their Lewis dot structures, they look a lot different than what you would just do by drawing it through the rules. And that's because by double bonding certain ones, it ends up improving the formal charge and becomes a better structure for that particular compound or polyatomic ion. All right, so as you can see, and then they drew it in the bent shape because of the 2 lone pairs, so indicating that it is going to be a bent shape molecule. But as you can see, the best and stable Lewis dot structure of chloride, not always the obvious one, but it does happen to make it have resonance in this particular case. Last thing I want to point out is benzene. Benzene's an interesting structure. It's this 6-carbon ring, okay, which has 6 sigma bonds, but it also is going to have some p overlap. And right here, if we look at this drawing, it shows that it has 3 pi bonds. And it's going to show resonance because those pi bonds could shift to the other carbons. All right, so the cloud does a better job of showing this. So you can see instead of it being just localized between the 2 carbons, like so, you know, or the opposite way, it actually delocalizes and forms a nice merged cloud on the top and on the bottom of the benzene ring. So benzene shows resonance, and what you might see also if you Google on or look in textbooks, yes, benzene is drawn like this, where you have the double bonds like so, okay, using like the stick figures, but sometimes you'll just see benzene that looks like this, where they put a big circle in there. They put the circle in there to show like those double bonds are actually spread equally across all of the 6 carbons in the ring, and it's showing resonance. So each one of these, you know, C to C bonds, put like a little dotted line between them because the double bond actually shares there. They all have bond orders of 1.5, like 1.5 bonds across each one. Benzene's a pretty interesting structure, and we talk about benzene a lot because benzene's one of the main nonpolar solvents out there, and they use it in lots of questions. So as you can see, it's just hydrocarbons, so the polarity difference is going to be 0.4s between the carbons and the hydrogens. So hydrocarbons are always nonpolar, and then we're going to talk about features of polarity and IMFs in the next unit in great detail. So knowing a little bit about the structure of benzene is helpful.